a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. Again, this lesson will presume that you have your multiplication tables memorized. If you don't, then seek a specialist at your school for special help. It's not a difficult task, but all of our following work will assume that you can recall these individual facts very, very rapidly and accurately. First, and as usual, let's build our vocabulary. When two or more whole numbers are multiplied, each of your multipliers is called a factor. The answer is called a product. So in this double multiplication problem we have down here, there are three numbers involved in the multiplication. So each of them we'll call factors. And the result, in this case, of 6 times 8 is 48, times 2 is 96. The answer we call a product. So product is a results of having multiplied. We cannot possibly underestimate the importance of knowing these vocabularies we are building. All future explanations in all future math courses will be done with this terminology. And along with a new vocabulary is a new symbology. The use of this small x is a usual way most people are familiar with an indicated product. Other ways that you'll encounter in the future is if we put the numerals in parentheses and shove the parentheses against each other with nothing in between. That will mean multiplication. So always between here is an implied multiplication. Or we might just put one of the numbers in parentheses. It might be sometimes the first and not the second. Usually this is not used so much, but it legally is possible. And you're probably familiar with using a dot raised to the middle to indicate multiplication. You can see this might be confusing with a decimal point in the future, so we'll try to avoid this except where the meaning is very obvious. Where we're using a letter to mean some number and we shove another letter or a constant against it, it means to multiply. So this will mean 3 times some number. If I had something like this, that will mean some number times some other number, but usually we will not write that dot. We'll simply show it that way. So as you can see, there are many ways of showing multiplications. As you move on, these two right here, or three really, will be the most common one. So do become very familiar with those. As you can see, the use of the parentheses shoved against each other is much neater than this approach right here. So more and more we're going to replace this by this in our notation. Do you recall the standard setup learned by most of us for multiplication? Without too much ado, let me simply work one with you watching over my shoulder. First, use guidelines if it will help you. With practice, of course, you won't bother with that. Then we started with the n digit of our bottom factor, 4, and we thought 4 times 7 from memory is 28. We could have written 28 here, 28. But traditionally we write the units digit here, 8, and 20 goes above the next column as an addition carry. Then we think 4 times 2 is 8, plus 2 is 10, no ones, and the 10 goes up here to the next column as a carry. 4 times 5 is 20, plus 1 is 21. Now we're through with these carries, and we're through with this ones digit. So we go next to the tens digit. 6 times 7 is 42, and we always start under our bottom multiplier. So 42, we'll put 2 here, and the 4 goes to the next column as a carry. Now we think 6 times the next one, 2 is 12, plus that 4 as a carry is 16. So 6 and the 1 to the next column as a carry. Now we go to the next. 6 times 5 is 30, plus the 1 is 31. Now we're done. For each digit in our bottom multiplier, we have a line of digits here. If I had 3 digits here, I would have 3 lines and so forth. Now we add these digits. We get 8, 2, 7, 3, 3, and this, our answer, which we now call the product of these two factors. Quite an involved process, isn't it? But much, much simpler than was used in the world, say, 800 years ago. There are many other setups that can be used to multiply, some of them rather clever and cute. Perhaps your teacher will show you one or two of the others, and in our extended lesson, I'll show you yet another one. But let's stay with this one, which is the basic one with which most people are familiar. You should practice quite a few of these until this becomes a very automatic procedure. See, it recalls multiplying, which means you need to memorize your table, additions, multiply, additions, and additions. So there's a lot involved here. For the sake of future discussions, it might be well here to remember that multiplying whole numbers is actually a shortcut for repeated additions. Originally, 3 times 5 was a symbol invented to mean take 3 of those and add them together. And you can see by that definition, 5 times 3 means something different from that. It means take 5 3s and add them together. And in both cases, we get 15. An interesting fact that surprises us as children, but in time we learn to live with it, that 3 times 5 and 5 times 3 are exactly the same process. Not the same process, exactly the same value. In fact, they are different processes, aren't they? This fact that I can multiply this way or this way and get the same results, later in algebra you'll refer to as the commutative law of multiplication. But can you see by this repeated addition law a problem like this? By addition gets completely out of hand. Can you even imagine having to take 495 of those and adding them together? That would take forever. So as complicated as our multiplication setup was, it's far simpler than having to go back to basics. Implied in this definition is another word that we'd best pause and consider more formally. The term whole number simply refers to the numbers 0, 1, 2, 3, 4, and so on and so on and so on forever. What we're basically ruling out here are fractions, square roots, pi, decimals, etc. So those are my whole numbers. No matter how we look at it, multiplication is an involved process, and none of us get overly thrilled at that. So wherever possible, we prefer doing it with a calculator. Do learn to do it by hand, though, because interestingly enough, that cuts down on the errors on calculators. You wouldn't think so, but that is fact. So on a calculator, each of these becomes a button. And of course, after punching each of those buttons, we want to know what the product is equal to. And so the equal also becomes a button. So on our calculator, we simply punch those as buttons. 4, 7 times 8, 2 times 3, 0 equals. And our answer, a very involved one, 1156, 11562. Now always remember, we might have made a mistake. So always clear and redo it. In a reverse order, if you wish, 30 times 82 times 47 equals 115620. So apparently we're correct. And of course, most of our problems in that mythical real world comes to us in verbal forms. A carpenter ordered 17 roof truss assemblies at $56 each. Can you see where this original definition is? 17 roof trusses at $56 each. That would be 56 plus 56 plus 56, 17 times. Rather than doing that addition, we do a multiplication instead. Now, a good practice at this point throughout your lesson is to do the problem first by hand and then check it with the calculator rather than the answer book. And if they don't agree, then use the answer page to check which one of those two is correct, hand arithmetic or calculator. So let me go through this very quickly. 7 6s is 42, carry the 4. 7 5s is 35, and 4 is 39. I'm done with that. 1 times 6 is 6, 1 times 5 is 5. Now adding 2, 15, 9, and I'm done. Now checking it with a calculator, and we got the same number. So do work by hand, always by hand, then check with the calculator. It would be nice in this course if you became good at both processes rather than using a calculator to avoid this. That will definitely hurt you in the long run. Avoid that. Let's look at another method of long multiplication, just for fun, really. We had just finished doing this particular problem by the traditional approach. And sometimes when we work a problem by the same method every time, we pretty soon get the feeling that that's the only way it can be done. Let's demonstrate that we could have done this multiplication by an entirely different setup. First, let's draw a rectangular box, a column for each digit in one of our multipliers. So we have a column for the 5, the 2, and the 7. Then one row for each digit in our second multiplier. So we have a row for the 6 and a row for the 4, and going from the top down. Do you see how we did that? Now, in each of these boxes, let's divide it by a diagonal. Each small box within the larger one can be located or denoted by two numbers. You could say this is the 2, 6 box, whereas this box is the 2, 4 box. This box, that would be the 5, 4 box. This box, 7, 6 box. So once you have set up such a box, let's take the name for each box. This is the 7, 6 box. Multiply those two mentally. 7 times 6 is 42. Put the tens digit in the upper portion and the units digit in the lower portion. Now, in the same manner, fill in every box. The interesting thing about this approach is it doesn't make any difference what order you work, whereas here, order was all important. So this box is the 5, 6 box. 5 times 6 is 30. This box is a 2, 6 box. 2 times 6 is 12. This box is the 5, 4 box. 5 fours is 20. Here, 2 times 4 is 8. 0 here if you wish. This box, 7 times 4 is 28. And here you don't have to worry about carries or adding on. It's just a flat recall of your multiplication tables. And if you had forgotten a multiplication tables, let's say you had forgotten that 7 times 6 is 42, you could stop, look it up, and write it down until you do learn it. Once you have filled in this box, these outside numbers, the multipliers, are no longer needed. Now notice we have diagonals going through this box. Let's call those diagonals number paths. So for our next step, let's simply ask ourselves to add all the numbers along each number path. So adding those gives me 8, which I'll write down below it. Adding the next number paths, we have 2 and 2 and 8 is 12. And if we have any carries, take it up to the next number path. So going to the next number path, we have 5 and 2 is 7. Then up to the next number path, 1 and 2 is 3. And then the next number path, 3. Now let's just read what we get here backwards, so to speak. 3, 3, 7, 2, 8. 33,728. That was the answer to our original problem. Isn't this neat? Now I show this to you not to necessarily show you a better method, but to get across the point that there are other methods. So if you're in a classroom or talking to a math tutor, be open for yet other ways of approaching a problem in mathematics. There are always many, many ways of approach. So let's do this once again to see if it really firms up in our mind. It's a very simple technique, really. Let's multiply this problem. Now, by the way, you might show this to a friend. People seem to rather like this. First, you want a box, and you want as many columns as you have digits in one of your multipliers. Then you want as many rows, in this case 3 of them, as you have digits in your second multiplier. Then you draw a diagonal through each one of these sub-boxes. Then we recall that each sub-box, let's say this one right here, is named by 2 digits. This is the 8, 3 box, and 8 times 3 is 24. So now simply recalling our multiplication tables, we fill in every box. This box is a 5, 3 box, that's 15. In any order you wanted. If you wanted to jump down to this box, 4 times 7 is 28. And in that manner, fill in all of these sub-boxes, as we've done here. And once the box is filled, the original multipliers you no longer need. Then you simply add all the digits in each number path. And if you get a carry from any one number path, you carry it over to the next number path. So adding down here is 5, here is 9, here is 7, 9, 14, 22. I had to carry 2, so it's 3, 7, 10, 18. Carry one more, 3, and 3 is 6, no carry, and 1. And our claim is that this 1, 6, 8, 2, 9, 5 is our answer. Let's check that on a calculator. Okay, so 485 times 347 equals 168,295. 168,295. This particular method is a handy one if you are trying to do long multiplication and you don't yet have your multiplication tables memorized. This will allow you to do the long multiplication while in the process of memorizing your table. If you need to fill in the table and you forget one of your multiplication facts, let's say you had forgotten what 8 times 4 was, then simply look it up on your multiplication tables. 8 times 4 is 32, and simply say 8 times 4 is 32 and write it over 2 or 3 times, saying it out loud each time you write it in, and then get on with the business of finishing the problem. It's a nice method, but there are several other methods equally as good as this, and you might ask your instructor if she or he knows of any. It's rather fun sometimes to take a fresh approach on a problem that might have been bothering you somewhat. While reviewing our multiplication facts, let's simultaneously get ready for algebra. Now, let's see what we mean by this phrase, let's get ready for algebra. Here's a simple algebraic sentence. The important thing about this at first is not being able to work it, whatever work means, but like any sentence, to be able to read it. This is a math sentence. Remember, a variable, in this case m, simply means some number. This little dash here means divided by. 3 is to be 6. So reading this, this says some number when divided by 3 is 6. And solving the equation means what number could have replaced this variable and made it true. And of course, our number fact simply tells us is 18. We know that without doing any work. We just know from memory that 18 divided by 3 is 6. However, this one is not so obvious, is it? What number divided by 45 gives me 56? So quite frequently, a textbook will start with easy problem where the answer is obvious right from the start. And unfortunately, sometimes that can mislead you because the process is not to know that 18 is the answer, but what can we do to get rid of this? Not just the 3, but the division as well, so the sentence simply says that m is something. So the fact we want to bear in mind from this lesson is this, that this mark is a division sign, some number divided by 3. So we ask ourselves, what process undoes dividing? So we note first that a multiplication always undoes division. So in this case, if I were to multiply this by 3, 3 times undoes division by 3. It's very important to realize that our focus point is on this, that this undoes this, and the 3 is almost incidental. But then also recall one of the fundamental laws of algebra. In algebra, one can multiply both sides of the equation, and those sides are called members of the equation in algebra by the same amount. So in this equation, this is one side, one member of the equation, and this is the other member. So if I multiplied this member by 3 to undo that division by 3, then I must also multiply the other side by 3. So this undoes this, leaving me with my symbol for some number, and the other side is simply 18. So this says, look, your number called m is 18. So now this problem, which is not quite as obvious, is simply a matter of asking, how do we get rid of this, or more specifically, how do we undo this division? So you undo division by multiplication, and since I'm undoing division by 45, I will multiply by 45. But then our multiplication law of algebra says that's okay, providing I multiply the other side by 45 as well. So this undoes this, and my math sentence now reads, my number m is 56 times 45. And if we do that arithmetic, this would give us 2,520. So by undoing this, then multiplying the other side by the same amount, this new sentence actually tells us how to find the value of that unknown number called m. So in algebra, if we see a simple equation where the number that's operating on the variable, the unknown, is dividing into it, we simply think to undo dividing, I multiply, in this case, by 148. Then algebraically, I recall that I have to multiply the other side by the same amount. Then this undoes this, and this says my S is 75 times 148. So in fact, my algebra sentence is now telling me what I must do to find the value of my variable. Isn't that simple? And if you wish, we even now have another way to go about our multiplication. And we have an answer by this new box method of multiplication of 11,100. So, however you do it, use this lesson as an opportunity to once again become strong and comfortable in multiplication. This is your host, Bob.